Today we are doing Lesson 2, Transformations with Absolute Value Parent Functions. So, sometimes when we graph with transformations, a graph is not given to us. Instead, we use already existing functions to get a starting graph to then move around. So, one example of an existing function is an absolute value function. So, when we don't have a graph, we start with a function, and that is a parent function. So we're going to look at the absolute value parent function today. So we have y equals the absolute value of x. You might have seen this before, but basically what this does, what those little bars do, is it makes any x value positive. It makes any x value positive. Okay, so if it's inside the absolute values, when it sends it outside the house, it becomes positive. Okay, so let's draw, we're going to do a little graph, or a table, oopsies, a table to kind of get our points. So if I plug in -2, -1, 0, 1, 2, I would get out all of those positives. So this becomes a positive, this becomes a positive. This is already positive. The following are already positive, so they just stay the same. So let's graph these points. There we go, that's good enough. Okay, so I've got -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. Okay, it's going to go through that corner all the way up there, and then it'll go through the corner up there. So it looks like a V. So this is going to be a straight line with a constant slope on both sides. So I'm going to write that. So it's a straight line with constant slope on both sides. Constant, same slope on both sides. So what's really cool about the absolute value function is that it mirrors itself. So if I give you one side of the graph and one point of the other, you can finish the graph. It's kind of cool. So our domain, remember, that's all of our x values. So remember, domain is left to right. So since we have arrows going in both directions, our domain is going to be -infinity to infinity. Our range, remember, that's all of our y values. So that's the bottom of our graph to the top. Well, our bottom of our graph is, remember, that's a y value of 0. Since there's an actual filled in point, it's a bracket, and it's going to go up forever and ever and ever, so we're to infinity. So that is the absolute value function. It's really cool. So let's actually start doing transformations on it. We're given that f of x equals the absolute value of x minus 2 plus 3. So if we know the parent function, we write transformations with the equation rather than f of x. So you know how in the previous lesson we had like f of x plus 2, and we would graph that? Well, what we're going to do now is we're going to actually take f of x, make it y, and put all of our transformations inside that parent function. Okay, so I want you to write this note. Actually, just going to type it. I think it's going to be easier. Okay. If we know the parent function, we write transformations with the equation rather than f of x. I'm going to make that look a bit nicer. There we go. There we go. So if we know the parent function, which we do, it's telling us the parent function by having those absolute values, we write the transformations in the equation. So it's the same process. What are the transformations in the equation? Well, we have minus 2, and then we have plus 3. So we have minus 2 on the inside, so then it means that we do the opposite. So that means we're going to go plus 2. And since it's inside, it's a horizontal. So it's a horizontal shift right 2. Okay. Now our plus 3 is on the outside, so it's going to be a vertical. Since it's on the outside, it's going to be what it says. So it's going to be a vertical shift up 3. Okay. So nothing changed. We're just now having an actual function versus f of x. So let's graph the parent function. So I'm going to draw our little table so we remember what our x and y values are. Oh, I'm going to redraw that. It looks really bad. Okay. Doom, doom, x, y, negative 1, oops, negative 2, negative 1, 0, 1, 2, 2, 1, 0, 1, 2. That is our parent function. So we have boom, 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 boom. There we go. Okay, there's our parent function. Now we're going to have a horizontal shift right and a vertical shift up 3. So our plus 2 horizontal goes to the x values. And then, so I'm going to do that. So plus 2, so we would get 0. So I'm just adding 2 to each of these. 0, oopsies, I'm ahead of myself. 1, 2, 3, 4. And then I have up 3. So I'm adding 3 to all of these. So 5, 4, 3, 4, 5. Oh, nice. So we can graph these. So we got 0, 5, 1, 4, 2, 3, 3, 4, and 4, 5. So there, wow, that's a really bad one, is our graph. I'm going to write new next to it so that way we can tell which one it is. So our domain for the blue graph is negative infinity to infinity because our arrows are going in both directions. Our new range, so that's the bottom of our graph, is at 3. It has a closed circle, so it's going to have a bracket all the way to infinity. So transformations can change your domain and range. Change domain and range. So let's go to our next page. We're going to use the parent function, f of x. You want to identify which parent function because that can change. To create an equation, we're going to graph it, and then we're going to find the domain and range of the graph. So, reflection over the x-axis. So, that means it's going to be outside, oopsies, outside my parentheses. Just like to kind of identify where it's being located. A horizontal shift right, well, horizontal means it's inside my parentheses. Right, so it's opposite, so minus 2. And then finally, a horizontal shift down, so it's on the outside, so it's going to be minus 5. So I kind of created my equation. I'm just going to take my parent function, which is f of x equals y. F of x, oopsies, equals this absolute value of x. So I'm going to have my negative on the outside, absolute value, x. I'm going to have my minus 2 on the inside. And then finally, my minus 5 on the outside. There we go. We just wrote our equation. So we're going to make our table really quickly. So x, y, -2, -1, 0, 1, 2. Okay. 2, 1, 0, 1, 2. So we're going to have a reflection. And since it's on the outside, it deals with our y. So I'm going to just do -2, -1, 0, -1, -2. Now we have our +2, which is on the inside, so it messes up with our x values. So we're going to add 2 to each because we're moving to the right. So we have 0, 1, 2, 3, 4. And then finally, we're going to have that -5, which makes us move down. So we got -7, -6, -5, -4. Oopsies. I was thinking too far forward. -6. Caught myself. -7. Okay. So I'm going to plot each of these points. So 0, -7. Ooh, I forgot to graph my parent function. I'll do it in lime green. Here is my parent function. Okay, now I can draw my new function, which is, I'm just going to tell it to you. Okay, fit it all. 0, -7. 1, -6. 2, -5. 3, -6. 4, -7. So there is my new graph. So my domain, how far left to how far right? -infinity to infinity. My range, remember that's bottom to top. Well, my bottom, it's going down forever, so it's -infinity. See, our range is changing. And our top is -5 with a bracket. So since we did a reflection, that made our range kind of flip-flop, meaning that instead of the lower number having the bracket, our higher number has the bracket. Okay, number 3. So we got a vertical stretch by 5. So that means that 5 is on the outside, and it stays true. We have a reflection over the x-axis, so that is on the outside. And then finally, I have a horizontal shift left, so that's going to be on the inside, and it's going to be the left, so the opposite, so +6. Okay. So my equation is f of x equals, well, I have a reflection, and then I have a vertical stretch by 5, and then I'm going on the inside, so bar, I have x, and then I have my +6, and then finally, end of my equation. There we go. X, Y, I'm going to make my table. So we got -2, -1, 0, 1, 2. So I have positive, 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 positive. Okay. So I have my reflection, which is purple. It's on my outside, so it deals with my y. So it makes all of these values negative. Okay. Now I have my times 5. which is on the outside, so it's going to deal with my y values. So I got -10, -5, 0, -5, -10. And then I have finally my +6, which is inside. It's a horizontal. So it's a horizontal shift left. So I'm, oopsies, not +6. Subtracting 6. So I get -8, -7, -6, -7, -8. Okay? Those horizontal shifts can get kind of confusing. If you get confused, just take a moment, step back, and look at it. Okay. So I'm going to start by graphing my parent function, which is that. And I'm going to end with -8, comma, -10, -7, -5, -6, 0, -5, -5, and finally -4, -10. Isn't that kind of cool? Just stretched it down. So, our domain, left to right, -infinity to infinity. Our range, finally, is, again, bottom. So since we're going down forever, -infinity. Our top of our graph is 0 because it's our y value with a bracket. Okay, so it's very similar to the transformations from lesson 1. The only difference is now we're using a real graph from a parent function that we are not given the physical graph at the start, but we're given the parent function equation. Okay, we'll finish the rest. So, you just learned one way to do graphing absolute values with tables. There is another way to graph these types of problems. So let's start by making our equation. So for number 4, we have a vertical shrink of 1/4, so that would be on the outside, and it would stay the same. A horizontal shift right 4, and then finally this would be outside, x up 2. And so our equation would be y equals 1/4 absolute value x minus 4 absolute value plus 2. So we can actually use this as these two numbers create this thing called a vertex. And so our vertex for this is going to be 4, 2. So this is the opposite, and this is the same. And then your vertical stretch, in this case, this is your slope of the line. So what I mean by this is if we graph 4, 2, so over 4, 1, 2, 3, 4, up 2, plot that point, and then do our slope, up 1, right 4. Yep, there's that point. And then we just do the opposite, up 1, back 4, because we know the shape of our graph. We can then now graph our line to make it be our absolute value. And so our domain will always be -infinity to infinity, and our range is going to be, oopsies, bracket 2 to infinity. And so to kind of prove this, we can do our table of values, x, y, -2, -1, 0, 1, 2, 2, 1, 0, 1, 2. Take our y values, multiply them by 1/4. Take our x values, add 4, and then take our y values and add 2. Some quick numbers would give us 2, 3, 4, 5, 6. Multiplying by 1/4 would give us 0.5, 0.25, 0, 0.25, and 0.5. And then adding 2 would just give us 2.5, 2.25, 2, just 2, 2.25, and 2.5. And what's kind of cool, that vertex I'm talking about is the middle of our graph because that's where our origin was. And so if you look, we have 2.5 right there, 3, 2.25, 4, 2, and so everything matches up. I think graphing your vertex and your slope is a lot easier, and what's really cool is that the direction of your slope and your y value of your vertex will give you your range, and your domain is always the same. So let's try it in number 5. So for 5, we have a horizontal stretch by 2, so this would be 1/2 because it's inside and opposite. Then we have a reflection over the x-axis, and then finally a vertical shift up 4. And so our equation is going to be y equals negative absolute value 1/2 x absolute value plus 4. And so our vertex is going to be 0, 4 because our h value is 0. And so 0, 4 is right here. And now our slope is taking both of these together and putting them together. So our slope is down 1, right 2. We're just, in a sense, going to reflect it over. We can actually do more points, so down 1, right 2, to get that graph. And there we go. And so our domain, always negative infinity to infinity, and our range, it flipped it of our parent function and was negative infinity to 4. Okay, let's go to the next page, our last page of our notes. So we have a reflection over the y-axis, a vertical shrink by a scale factor of 1/2, and then a vertical shift up 2. So let's think about this for a moment. Here's our parent function. Okay, if we reflect our absolute value over the y-axis, well, whatever maps here goes here. So our graph would just become the absolute value graph because it is symmetrical. We can still write our equation y equals 1/2 absolute value of negative x plus 2, and our vertex is going to be 0, 2, but our slope is just 1/2 because that reflection over the y-axis doesn't do anything. And so let's see, okay, so our domain is negative infinity to infinity, and our range, because we don't have a reflection over the x-axis, we're going to say is going to be bracket 2 to infinity. Let's see if that's true. So our vertex is 0, 2. Our slope is up 1, right 2, up 1, right 2. Reflecting them over will give us this graph, which domain's correct and our range is correct. Okay. I want you to try to write the equation for number 7, and you can pause the video. Hopefully you did actually pause the video. So we have a horizontal shrink of 1/3, so that's where we would do the opposite. A reflection over the x-axis, so that's going to be on the outside, and then a vertical shift up 4. And so our equation would then be y equals, because we're creating an equation, oopsies, I forgot my negative, absolute value of 3x plus 4. And so we can find our domain and our range. Well, because of that negative, it's going to flip that range. The reason is because these affect our y values to 4 of our vertex, because our vertex, oopsies, is 0, 4. And our slope is going to be negative 3. So 0, 4, oopsies, not enough, 0, 4. Our slope is down, oopsies, right 1, down 3, reflecting it over. We can get more points reflected over. to get this graph. Now, what's kind of cool with the absolute value is that a horizontal shrink can look very similar, or looks identical to a vertical stretch. And so that's why it might be a little confusing right here. And so there is graphing the absolute value function. Let's finish these problems. So given the parent function, f of x, create a formula. So this is actually review from the previous lesson. Because we're not using the absolute value, we're just using f of x. Create a formula for the following transformation. So a vertical stretch of 3 and a reflection over the y-axis. So vertical stretch of 3, that's outside because it's vertical. And then a reflection over the y-axis. Well, since it's a y-axis, it's on the inside. Okay, let's try number 9. Parent function, f of x. So again, we're working with a general function. Using a vertical shrink of 1/2, so that's on the outside. A reflection over the x-axis, so it's going to make that as a negative 1/2. And then a horizontal shift left 3. So that means we're going to do, because usually that would be -3, but we want to do the opposite for our equation. And so just in case you need the color coding, vertical shrink of 1/2 is this piece. The reflection over the x-axis is the negative, and the horizontal shift left 3. Why don't you pause the video and try number 10? Hopefully you did. So we have our f of x. We have a horizontal stretch of 2. So that's going to be on the inside, it's the opposite, and then a vertical shift up 3. So here are all the pieces. Please come with your questions, and we'll go over it in class.